where I need to introduce a second type of polarity, molecule polarity. Molecule polarity, like bond polarity, means that when you look at what's happening on each side, there is a difference or a lack of difference. Okay, so bond polarity, it specifically looks at the electronegativity difference. And this is to describe how the electrons are shared in a bond. So electrons shared in one bond. So the bond polarity is unique to one single bond, where the shape of the molecule is how all of the bonds are distributed around the center atom. So this is how the bonds are distributed around the center atom. So there's a lot of chemistry. There's the Vesper theory, okay? We won't go into all of this, but we'll get this idea down. So Vesper stands for valence shell electron pair repulsion. So in a molecule, we identify the center atom, and it typically has the lower electronegativity, and it forms the most bonds. And we take a look at how these bonds are distributed around the atom. Valence electrons are arranged as far apart from each other as possible to minimize the electron to electron negative repulsion. So how far apart can we spread these bonds to limit the negative to negative repulsion? So here we go. If it's a nonpolar molecule, we have a symmetrical distribution of the bonds. They are equally distant around the entire molecule. Where polar molecules, there's a lopsidedness to it, so there is a definite difference. Polar molecules have an asymmetrical distribution of the bonds. So we have a little mnemonic, OSNAP. So OSNAP, if our bond distribution is symmetrical, then it's nonpolar. If our bond distribution is asymmetrical, then it's polar. So here's how we're going to look at it, is we look at the vectors, and we'll keep it simple. We're just going to look through each of the axes. So here we go. First, structure. So if I look at this molecule through the x-axis, right? Bond and type of atoms I see above the plane looks to be the same below the plane. It seems to be a mirror image. So I'm going to say that this has symmetry. Then I take a look at the same molecule, but now through the y-axis or the y-plane. And what I see bond-wise and atom-wise on the left seems to mirror what I see on the right. So I see that this is symmetrical. So I need to keep going. There is a third axis, the Z. And so that's the one where you have to look at it more at an angle. So what I see in this upper left quadrant seems to mirror what I see on the bottom right quadrant. So it seems to have symmetry. So when I find that no matter which way I look at this molecule, it seems to show symmetry through around the entire thing. So in the OSNAP, right? In the OSNAP, it seems to be symmetrical on all three planes. So this would be a nonpolar molecule. Now, taking a look at the next structure, the sulfur and hydrogen. When I cut this down the y-axis, what I see on the left seems to be a mirror image of what I see on the right. So there's symmetry. We have to look at this through the center atom, which is sulfur. So now when I cut this through the x-axis or plane, and when I look to see the contents above the plane versus what's below, it doesn't match. So that is asymmetrical. And once when I find at least one plane is asymmetrical, all I have to do is find one, then I know it is definitely an asymmetrical molecule, so it's polar. So this would be a polar molecule. Okay, taking a look at this next one. Here we go. If I cut this down that y-axis and I compare what I see to the left compared to the right, it's not a mirror image. It lacks symmetry. So in my snap, right away, I found an asymmetrical plane, so I know that this is a polar molecule. Taking a look at the next one. So if I cut this down the middle, looking at the y, it seems the left seems to match the right, so there's symmetry. If I cut this down what we would say traditionally is the x-axis, what I see above seems to mirror what I see below, so there's symmetry, have to keep going. And when I cut this through the z-axis, the angle one, what I see in the upper left seems to be a mirror image of what I see on the right, so there seems to be symmetry. So when I look at this molecule through all three planes, there seems to be symmetry. So when I think about the O-snap, because it's symmetry in every direction, I would say that this is a nonpolar molecule. Let's take a look, a couple more examples. This molecule that contains the fluorines. Comparing the left side to the right side, symmetrical. Cutting it through the x-plane, what is above seems to match what is below, symmetrical. And then cutting this through the z-axis, what I see in the upper left compared to the lower right seems to be a mirror image, symmetrical. So I would refer to this as a nonpolar molecule. Last example. If I cut this molecule down the center, so that would be through that double bond, what I see on the left seems to mirror the right, so it's symmetrical. When I cut this through the x-axis, what I see above the plane seems to match below the plane, so it's symmetrical. And when I cut this through the z, which is this guy here, what I see in the upper left plane seems to match what I see in the lower right plane. So I'm going to say it is symmetrical. So this would be an example also of a non-polar molecule. Keep it simple. Just look at them through the axes.